Yeah, thank you, Ingmar. Indeed. So apart from all the other things, what Ingmar mentioned, one of the things was the mixing or the local gradients. So let us dig deeper a bit in the gradients in the bioreactor. We will start with a very simple example of a coffee cup where you are pouring milk in coffee, and you would expect that it will actually mix immediately. But you know that if you don't stir it very well, it takes much more time to actually completely mix, which means the gradients, even at that small scale, exist. And by the gradients, we mean the difference between concentrations across the whole reactor system. What we did in order to confirm this, in 2017, we did a measurement campaign on a wastewater treatment facility in Netherlands in Eindhoven, using a crane with multiple sensors attached to the crane, and we went deep into the reactor to measure dissolved oxygen and also other measurements. But if we go forward in the next slide, we will show how it looked like. So we attached several sensors with the crane, and we went deep inside the reactor, and not only deep, but we also measured across the whole width of the bioreactor. And we observed that actually dissolved oxygen is not really constant, but it's very varying, and it means that there are really gradients existing in such a big bioreactor as well, even though in the very much aerated zone where the aeration was really happening. So in this graph, there are two graphs which are two different locations in the bioreactor. On the left side, you see dissolved oxygen across the depth of the bioreactor and the width. The blue color shows you the dissolved oxygen, shows the low dissolved oxygen, and the higher or the red or the green colors are showing you the higher dissolved oxygen concentrations. And you can see clearly that there's a 40% difference between the top and the bottom dissolved oxygen concentrations, which is a big gradient at the same location. And then on the location C, it's not only along the depth, but it's also along the width of the bioreactor, so the diagonal. So almost oxygen gets doubled from going right to the left in the bioreactor. This was confirmed with the CFD simulations, which showed almost similar gradients arising because of the hydrodynamics of the system in the bioreactor. Okay, and this is also not the case only for one type of bioreactor, but this is almost the case for all type of bioreactors. Here you see a very different aeration system. The system we saw earlier was more of a plate diffuser system at the bottom. Here you see the surface aerators, which are at the top. And what you see on the right side is a figure showing oxygen concentrations and ammonium concentrations. You see clearly that there's a higher concentration of oxygen near the top and lower concentrations near the bottom. Whereas in ammonia, eventually, of course, it leads to low concentrations near the top and higher ammonium concentration near the bottom. So it means that it really depends on your system. It really depends on your operations. How are you really operating your bioreactors? We have also done some off-gas measurements to further confirm this. Our colleague, Dr. Giacomo Bolandi, has actually done the measurement campaigns in two different plants in Italy, one in Florence and one in Rome. And in both conditions, what we did was we put gas hoods across the length of the bioreactor and also along the width of the bioreactor to see, is it only along the length when the reaction is really happening along the length of the reactor, or is also the case when it comes to the width of the bioreactor. So normally what you would expect is that, okay, your influent is coming in from left and going to the right, and it's like continuously causing a reaction, and you would not expect a lot of variation between the radial or along the width of the bioreactor. But what we observed in both the cases was that there was always a difference between location 1 and 2, or location 3 and 4, location 5 or 6 in both the cases. And for example, in the case of Rome, there was like almost 20% difference between the oxygen efficiency of location 7 and 8. Which just tells you that there are actually differences when it comes to dissolved oxygen, or actually similar, the other variables as well will eventually have variations in the system. Okay, so this makes things a bit more tricky, because what does it tell you? That, okay, where should we be placing our sensors? And once you have put your sensors in a certain location, how would you interpret it? Are you putting your sensor in a very good location where you expect a value or a measurement which is representative of the whole system? Or if not, then how would you interpret it? How would you derive these conclusions out of your measurements? But what is more certain is that every bioreactor has gradients. We got to know how we can quantify the gradients, how we can measure the impact of those gradients on the performance of the bioreactor. And it actually varies from one plant to the other. It also varies how much flow is coming in, how much aeration you are putting in. So it's really plant dependent feature of a bioreactor.